Welcome to the virtual presentation of our paper, Sunstone, Navigating the Way Through the Fog. The motivation for our paper is the emergence of fog computing. And in fog computing, fog sites provide storage and virtualized computing resources in close proximity to the user. And this enables different types of upcoming applications such as AR, VR or IoT analytics. What we ideally want to have is multiple fog sites that reside in different autonomous systems on the path from the user to the cloud. And what this entails is that these fog sites in the different autonomous systems are owned by various stakeholders, for instance, different internet service providers. And what we ideally want is to have a loose coupling between those users and fog sites. And this federation between users and resources across these administrative domains requires the definition of several interfaces as shown in the picture here. And this picture sort of illustrates the reference architecture that we consider for the remainder of this presentation. In this reference architecture, there are two important functionalities. For one, this is the discovery of fog resources, and on the other hand, the orchestration of those fog resources. What we see today, however, are mostly single cluster solutions or centralized approaches. We see a very tight coupling between the services and the users, and most importantly for our contribution, the discovery remains limited because existing approaches assume that either fog sites are known beforehand. There are a lot of discovery resources whose scalability is severely limited, and other approaches such as peer-to-peer approaches tend to suffer from topology mismatch. In this paper, we present Sunstone, which is a novel approach for the joint discovery and orchestration of fog resources. Sunstone works across multiple administrative domains. It is compatible with existing infrastructure and as such requires no modification to existing network middle boxes. We use different combinations of on-path and off-path discovery approaches, and we leverage two existing protocols present in the global internet infrastructure, that is DNS as a globally scalable database and BGP as an information exchange protocol. And this discovery functionality is embedded into an end-to-end orchestrator for fog resources. Now, how does our system look like? This figure shows the high-level system overview of Sunstone, which consists of two parts, discovery and orchestration. And the result of the first part, that is the discovery, is the basis for the subsequent orchestration that ultimately decides where applications will be run. As I said in the introduction, we consider different approaches for discovery. And the first one is on-path discovery. So in on-path discovery, the fog resources are located on the actual network path between the users and the cloud. For instance, this could be on network middle boxes that are directly involved in routing or forwarding of traffic. And in on-path forwarding, our discovery approaches works by sending probe packets, which are recognized by fog sites. We do so by sending those via a modified trace route. I will go in a bit of more detail later how this is done. We include a custom payload in the trace route packets. And the fog sites then reply to these traceroute packets with more information, for instance, on the type of fog that is present. Second is limited off-path discovery. So here the fog sites are not on the direct path, but they are within the autonomous systems that are traversed. And here what we do is we provision information about the fog sites via DNS NAPTA records, which is a naming authority pointer. Why these kinds of records? Well, it is more flexible than other type of records, for instance, SRV records. So NAPTA provides, for instance, support for regex. There are different possible values. For instance, we could define multiple service entrance points. And this off-path discovery is applied on each intermediate hop of the traceroute result. That is, we query DNS records for each of those intermediate hops. So in doing so, we first, of course, perform an IP to autonomous system translation. Then the PTR records actually resolves the network, and then we can use the NAPTA record query to gain information about fog sites in this autonomous system. And lastly, we have full off-path discovery. Their fog sites are located in autonomous systems that are not traversed on the direct path. And a naive approach where we could also use DNS in crawling over all domain names clearly would not scale. Therefore, we need a bit of a different approach here. And what we do is we use so-called BGP community strings. More specifically, an extension to the standard that's called large communities. And this enables us to announce additional information about prefixes to BGP peers. And we use this in conjunction with DNS queries. Now you might ask how many autonomous systems should be traversed, and this can be defined by a parameter k, and there's clearly a trade-off here between the path length and the number of fog sites that I can discover. So intuitively, it makes sense to kind of limit this path length, and one naive heuristics would be to limit k to the baseline, which is the distance from the user to the cloud application. Although, of course, in practice, the number of hops and the full end-to-end latency, there is oftentimes not a direct correlation between the two. And the orchestration part of Sunstone basically takes care of managing the topology of the applied resources according to customizable policies. So most importantly, what I mean by orchestration is the placement decision. So once I have discovered a suitable fog site, of course you have to make a decision where the applications are actually run. And the input for the orchestrator part is, for one, the discovery result obtained in the previous step, and an application descriptor, which describes the components of the application and contains the placement policy. So for instance, we could define a policy where we would choose the fog site to which we have the lowest latency. If we think of a data analytics application where we, for instance, process different sensor data and apply some form of filtering on them, we could decide based on, to find an optimal aggregation point. And the orchestrator exposes an API to manage the life cycle of those applications. And we support different kind of executions environments, for instance, Kubernetes or OpenStack. We implemented these concepts in a proof of concept implementation, and in this figure here you see the two functional domains, that is discovery on the right in light blue and orchestration on the left, shown in green here. And all the different components are implemented using a microservice style approach. Most of the functionality is implemented in Python 3 using Flask as a framework. Some low-level code is written in C++ and integrated into the Python execution environment. We use a distributed key-value store to persist data at runtime. Communication between the components is realized via RabbitMQ. And the components that are running on the fog side, that is in this in the dashed rectangle you see here, those are fully decentralized and use Kubernetes for their deployment. The discovery agent provides a REST-style API for front-end access to all discovery-related functions. The core functionality, as I mentioned in the systems design overview of the discovery part, is that we invoke trace routes and then perform subsequent discovery steps on those trace route results. We use a special implementation of traceroute, which is the so-called Dublin traceroute, which is robust to nuts that may be present between the hops. We include a custom payload, which is encoded using protobuf, and the snooper, as mentioned before, detects the traceroute packets and returns data to the discovery agent, for instance, the type of the Fox site, the distance to the Fox site, and the API entry points for the user. For the orchestration part, we have a so-called Orchestrator, the Fog orchestrator that is responsible for the lifecycle management, and it executes those discovery processes and evaluates the placement policies. So policies in this context are abstract implementation of the decision logic and not application specific, which means that they can be reused. So in literature, there is for this classification by Hong et al., which classifies policy with regards to multi-tenancy of applications and users. So for instance, we have a SASU, which would be a single application component for a single user. We can extend this to a single application component with multiple users, and so on and so forth. And then, based on those abstract implementations, one can specify or implement concrete policies. For instance, I could come up with something called nearest SASU, which means I have a single application component to place used by a single user, and for this I want to find the nearest Fox site, for instance, in terms of hop count. And then we have the KA agent, which is the gateway to the Kubernetes at the Fox site, which basically translates this orchestration decision into Kubernetes API calls. For the evaluation, we evaluated Sunstone on an internet scale using real network topologies. And this figure shows how we create the network graph and with what data we enrich it to perform our evaluation. We start by a list of autonomous systems and add metadata from a public database about these autonomous systems. And second, we leverage so-called RIPE Atlas probes, which are operated by volunteers and allowed to collect information on connectivity and reachability of network nodes. What we first do is we filter the autonomous systems. So for simplicity reasons, in the evaluation, we only considered autonomous systems that are in Germany, and at least one of the probes within the autonomous system should be reachable via NAT to support ICMP trace routes. In total, we have 107 autonomous systems in our evaluation. And then we construct a graph of all these autonomous systems as follows. So we perform a trace route from the cloud location to all probes, aggregate those by IP on an autonomous system level, and enrich them with path that exists but were not taken by our trace routes, because we have no influence about the path that are actually being used during the trace routes. And the result is a graph of autonomous systems whose edges represent the connections from cloud instances to all the relevant probes inside those autonomous systems. In the first part of the evaluation, we study how the end-to-end latency is reduced as a result of the discovery of a Fox site where the user service will be executed. So in this part of the evaluation, the RIPE probes represent location both of users and Fox sites, And we operate on the assumption that either 5% or 10% of the autonomous systems contain at least one fog site. We validated this assumption via an empirical pre-study that showed that beyond 10% we have very little further reduction in latency. And on these autonomous systems, we now do the following. So one probe which within the autonomous system is randomly selected, and this is chosen to represent the fog site. And the remaining probes represent users. And as a baseline, that is the cloud, we use AWS infrastructure, more specifically the EU Central 1 region. In DNS-based discovery, we determine the shortest path from each user to the cloud instance using traceroute. We then check the autonomous systems that contain fog site on this path using the NAPTA records. And for BGP-based discovery, we assume that the information about the fog site has been disseminated. And the K value, that is the path, the length of the autonomous systems path, is determined for each path from user to each fog. Here's the result of the discovery. So on the right-hand side, you see a CDF graph of the latency. And on the left-hand side, there's a table with the statistics on the average latency and the average reduction compared to the cloud baseline. For DNS only, we can already see some reduction in the average end-to-end latency. However, we also see that much greater improvements are possible using BGP. Here we see for DNS, we use 10% of fog sites. For BGP, we perform two different evaluations for 5% of fog sites and 10% of fog sites. In the second part, we look at how the results of the discovery improve if we add the orchestration component. So remember, in discovery only, we simply choose the fog site with the shortest path. But this path length does not necessarily correlate with the actual latency we have on the path. And in this part of the evaluation, we compare this discovery only with the orchestrator component, implementing this nearest SASU policy that I described before. Here you see the CDF graph of the latency for precisely comparison. In these cases, we use, for both the discovery and for the orchestration, we use 10% of fogs, and we see that with this application component enabled, the average latency further drops from about 17 milliseconds to below 7. Lastly, let me quickly wrap up this presentation with some discussion and possible future work. So in our implementation, discovery was done in a synchronous way, meaning it was triggered at the time when the application migration or placement is decided. Of course, in the future, we could also perform this in an asynchronous way, for instance, periodically run the discovery and then cache the result. For the distribution of BGP community, this of course only works if the community strings are not filtered. In practice, this heavily depends on the policies of internet service providers. There might also be a delay in the distribution of community strings, which we have not considered. In future, this could be addressed by performing so-called DNS preloading. That is, load all the records from each prefix that is routed in the internet beforehand. What we also did not consider is path asymmetry. So this would occur mostly when traversing multiple autonomous systems and hot potato routing is used. In our case, we operated under the assumption that we only have symmetric paths. And with this, I would like to finish my presentation and thank you all for your attention.